Hello and welcome. I'm Rachel Burson. We'll wait for the video to load in. I'm happy to welcome you today to the final workshop of the summer of 2022. I was almost going to say 2023. And today, the workshop leaders, it's very special because both of them are alums of the RI Summer Scholars Program. And through their sharing in the program, they've helped to build cohorts, they've built networks, and they continue to contribute. What I've seen from the scholars over time is that then they go on to be the next generation of innovators and leaders. And I am so excited that perhaps in the future years, those that are going to watch this video, Neehar or Rayna may be your mentor, your supervisor, your boss, your guide, and they're sharing their passion in robotics with us today. And specifically, they want us to help us explore autonomous systems, autonomous vehicles, and give us some insight. So this workshop is specifically designed to ground you, to give you some awareness, and they've provided some resources to continue to explore. So we are delighted to welcome Rayna and Neehar and thankful for their sharing of time and their preparation to share their passion and expertise with you today. Welcome both.
So much, Rachel.
Thanks, Rachel, for the introduction. I'll do a quick intro of myself and then turn it over to Neehar. But as Rachel said, we're both alumni of the RISC program. I just did it this past year and the year before. I'm a rising senior at Colby College studying computer science. I was in Dr. Stephen Smith's lab for this year and the past year, working on pedestrian path prediction and reorientation, specifically for blind pedestrians, urban crosswalks. So turn it over to you, Neehar.
Thanks. My name is Neehar. I'm a second-year PhD student at the Robotics Institute. So I was a summer scholar in 2020. So I've had a wonderful experience, and through RISC, I actually got introduced to this topic of autonomous vehicles. So hopefully by the end of this talk, you guys have a kind of understanding of how autonomous vehicles work and how they can see the world. So with that, let's first ask the most basic question: what are autonomous vehicles? So autonomous vehicles are agents that act in the world, that have the ability to see, and this is through perception. They have the ability to think, and they can predict how other agents in the world will act and react to themselves, and they're able to act in the world. So given all this information about perception and prediction, we need to go and move in the world. Right? So an autonomous vehicle isn't very useful if, given all the sensor data, we can't get from point A to point B. So these are the three pillars of what makes an autonomous vehicle. And here's a really cool video from a local startup here in Pittsburgh called Argo AI, showing off what autonomous vehicles can actually do in the real world. So here we see we can detect a bunch of objects in the scene. We're drawing blue boxes around these things. We're predicting where they'll go in the future. These are the dotted blue lines. And we're trying to plan out a trajectory for ourselves. This is the solid blue line. And this is a really difficult, unprotected left turn. So here we're taking the turn. We're predicting this pink car is going to stop and yield for us. And we're able to successfully execute the maneuver. So these are a lot of the components which make autonomous driving so difficult, but it's also what makes it such an interesting problem, is because we need to basically build in something that us humans, we can do really easily. So all of us can drive quite easily, but baking in that intuition and knowledge of how to deal with complex situations is one of the challenges of working with autonomous vehicles. So the important thing to note here is, when you think of autonomous vehicles, the first thing you think of is a car driving in the streets. But this is not always the case. So from Amazon, we have their tiny little robot. It's called Amazon Scout. And this Scout robot is going to, in the future, help deliver your Prime packages. So this is a small sidewalk robot that has to navigate, bumpy sidewalks and, debris in the way, and it needs to get from the warehouse to your house. Next, we see something from a company called Neuro. Maybe you've seen a couple of their advertisements on TV, where they've partnered with Domino's, and maybe the next time you order pizza, You won't get a delivery driver per se, but you'll get a delivery robot like this one from Neuro. And I think the most exciting avenue for autonomous vehicles right now is actually in trucking. So trucking is actually a lot easier because we spend a lot of the time on the highway. The highways are very standardized and it's very easy to travel at consistent speeds. So this is an area of innovation where I think we'll see a lot of rapid progress, where autonomous vehicles are going to quickly help the trucking industry. So autonomous vehicles really do come in all forms. Yeah, but I guess the important thing is, all autonomous vehicles are not created equally, and we need to understand what autonomy actually means and how we quantify autonomy. So there's a generally accepted scale of from 0 to 5, where the first half of the scale is really putting the control in the hands of the human driving the vehicle. So the responsibility is still and the decision making is still mostly on the human. And then once we get to the later half of the scale, autonomous vehicles really are the brains and control of this entire system. So at level 0 autonomy was basically all we had up until the late 1990s. So I remember my dad had a 1999 Toyota Camry. And that basically all it could do was drive. This is back in the days when we didn't even have CD players. We had tape players. So this is the majority of cars during this era had no automation. And this started to change in the early 2000s with things like adaptive cruise control. So now you could set a speed limit and your car would detect other vehicles in front of you, and it would make sure that you didn't collide into them if they slowed down. Next, we see in more recent years, in the mid 2010s and early 2020s, we see things like partial automation from Tesla Autopilot. So now we have vehicles that are able to navigate by changing lanes, by driving under pretty strict supervision, but they're able to accomplish a lot of tasks on their own. And this brings us to where we are today. So really, we're somewhere between level 3 and level 4 automation. And this really means that we have a safety driver that is constantly monitoring what the autonomous vehicle is doing. And we need to make sure through strict safety guidelines that's not making unsafe maneuvers. So right now at level 3, this conditional automation is really about kind of giving autonomous vehicles a little bit more control. And as we go up the hierarchy here towards full automation, we'll gradually give the autonomous vehicle more control. And a big part of this is building trust in these autonomous systems. So between level 3 and level 5, this is really a gradual way in which we can build trust that these systems are actually safe. So this is a really exciting time for autonomous vehicles, because a lot of the companies, which you may have heard in the news, are actually they're starting up their own public-facing driverless services. So, for example, in 2020, Waymo opened a driverless service to the general public in Phoenix. So just like how you can open an app on your phone and you can call an Uber, now you can, instead of calling a human driver, you can call an autonomous driver. And we're seeing this across the industry. So Argo AI, again, the local Pittsburgh startup, has begun driverless operations in Miami and Austin. And I don't know if you guys have ever been to Miami or Austin, but those are some pretty challenging roads to drive. And the drivers there are quite aggressive. So being able to operate in this autonomous fashion is really a testament to the time and effort that the industry and academic partners have really put into trying to solve this problem. And lastly, we see Cruise is doing something similar in San Francisco. So we have a lot of different players in this industry, and everyone is starting to roll out public-facing autonomous experiences. And I think this is super exciting because, as you can see, this is happening today, or this is happening in the last few months. So there's a lot of focus on autonomous vehicles these days, and it's clear why this is such an exciting time. But obviously, things are not always perfect. So this is a picture from a news article a few months ago about how crews, their entire fleet in San Francisco, lost connection to the internet, and they kind of just all stalled in the middle of the street. So this is not ideal, but it's much better than executing unsafe maneuvers. And thankfully here all these vehicles safely stopped, right? But there's still a few kinks to work out, and I think this is kind of the overarching story of autonomous vehicles. We've been making progress on this for decades, and I think the final product is finally within reach. I think we're making great strides, and this is a great example of some of the issues with the current systems, but also opportunities for improvement and building out safe autonomous systems for everyone. Okay, so now we're at CMU, so I can't give a talk about autonomous vehicles without talking about CMU's long and storied history with autonomous vehicles. So in 1986, CMU had the NavLab 1, and this was a big RV. And it had massive amounts of compute, and it had the latest generation of sensors, and it could travel at a top speed of 20 miles an hour. And now we look at the self-driving service we have today, and this is almost shocking to see how far we've gotten. So this was the NavLab 1, and just 4 years later, the same team came up with the NavLab 5, and this car was able to traverse the entirety of the United States from Pittsburgh to San Diego, and it was able to do it 98.3% autonomously. So again, this is going back to the fact that driving on highways is significantly easier than driving in cities. So I think it was like a 2,900 mile trip, and they only needed to intervene manually for about 50 of those miles. So here's the shocking thing. So we've been able to get 98.3% of the way from Pittsburgh to San Diego since 1990. 1990 was 32 years ago. So for the last 32 years, the industry and academic community has really been focusing on really capturing that last 1.7%. And I think that really speaks to the challenge of really solving autonomous vehicles and really making this a widespread phenomenon. And obviously we have the DARPA Grand Challenge, which was a pretty big event in which the government funded academic teams to go and build robots that could traverse the desert. So the first challenges were basically traversing a 210-mile course in the Nevada desert, and this was challenging because of the environmental conditions and the driving conditions. So obviously driving on pavement is totally different from driving on sand and loose soil. So this was another pivotal moment in CMU's history with autonomous vehicles. Okay, so this is kind of the precursor and history of autonomous vehicles. But now to answer the question about how do autonomous vehicles see the world, well, it's pretty simple. They see the world with sensors. And I guess for the rest of this talk, I'm going to be talking a little bit more about these sensors. So the three sensors to keep in mind, and these are the primary sensors which are often deployed in autonomous vehicles, are cameras, LiDAR, and radar. And we have a huge number of sensors on these vehicles. And as you can see, with these sensors, we can have a 360-degree view of our environment. So a lot of these sensors also have overlapping views, so we can get redundant information. So first, let's talk about cameras. Cameras are the thing that's most similar to natural vision. So when we drive, we have two sensors right here in our head, and we use these two sensors to drive. And cameras provide really dense color information. So this is great for telling the difference, for example, between cars and police cars. So with cameras, we can actually understand the world around us just as humans do. But the issue here is there's a lot of background pixels. So when I'm driving a car, I really don't need all this information about the buildings. I really don't care about the color of the sky. And as you can see, this is a majority of the frame here. And you could argue that you really don't need to know the color of the pavement here, because this isn't really essential for driving. And another challenge here is that you really don't have a good sense of depth. So if I look at, for example, this car in front of me in the top middle panel, how far is this car from my vehicle? Is it 2 meters away, 5 meters away, 10 meters away? It's a little bit challenging to give an accurate estimate here. So cameras alone are insufficient to solve this autonomy problem. So now we have complementary sensors. Now we have things like LiDAR. So LiDAR is the short form for light detection and ranging. And this is a spinning laser that sits on top of the vehicle that can give you good estimates of depth. So it sends out a laser, and when it hits an object, you know exactly how far that object is from you. But one of the challenges here is that this LiDAR gives you really good information close up, but it's really hard to get accurate information at faraway distances. So you get a sparse number of points, 50 or 100 meters away. So this is one of the limitations of the current generation of sensors. So how does LiDAR work exactly? Well, LiDAR provides 3D information about a scene by using spinning lasers. So it has a column of spinning lasers, and you can imagine these lasers, they shoot out a pulse, and we start a timer. And once we start this timer, we wait until we get a pulse back, right? So we expect that this light will reflect off some object, and we'll, after some period of time, we'll get a reading back. And since we know the speed of light is a constant, and we know the time that it took for this laser to go hit an object and come back to us, we can get an estimate of the depth of that object or the distance of that object from our vehicle. So this is extremely important for having a robust 3D understanding of the scene. So the problem with conventional LiDARs, as I mentioned, is we have really sparse LiDAR returns at range. But through some recent innovations, we have LiDARs that are much denser. So if you look at this image, this almost looks like a black and white image you would get from a camera, but in fact, this is actually coming from a LiDAR sensor. So we have a few. This is a different form of LiDAR rather than the standard LiDAR that's able to give much denser understanding of the world. So it's exciting to see where the sensors and innovations in sensor technology can help push algorithms and the technology forward. So I'll just let this video play out and give you guys a chance to look at this output. And I think this is one of the coolest things to come out of the immense amount of investment and innovation that's going on in the autonomous driving industry. Okay, great. So we've covered cameras and we've covered LiDAR. And then the last sensor we want to talk about is radar. So radar stands for radio detection and ranging. And this is different than the other sensors in that it uses a different form of the electromagnetic spectrum. So instead of using light waves, we use radio waves. So this is great because it helps us detect shiny metal objects. And one of the things which we see a lot when we're driving are these shiny metal boxes, and these are cars and trucks and vans and buses. So this is great for detecting those things. And different than LiDAR, radar actually works quite well in the rain and the fog. So imagine thinking back to LiDAR. How does LiDAR work? LiDAR is sending out a pulse of electricity. So it's quite difficult to actually get good estimates of the distance when your light beam is actually being scattered by fog or rain. So this is where radio waves work really well. Another really interesting thing about radar is that if we position the radar kind of low and close to the ground, we can actually send out a pulse. And if you're in a traffic situation here, the LiDAR can actually bounce underneath the car in front of you, and it can help detect, 2 cars in front of you. So this is great for a traffic scenario where, for example, 2 cars in front of you brakes really heavily, right? So if you're able to detect that car, you have advanced notice about the braking of the car in front of you, and you can perform a more safe maneuver. So this is why radar is great. But unfortunately, radar alone radar directly produces really noisy sensor measurements. So we need to do a lot of post-processing to make radar viable and robust. So this is one of the downsides of radar. But again, as I mentioned, we have a whole bunch of sensors on the car, and it's often claimed that autonomous vehicles are over-sensored, which means we have way more sensor data than we know what to do with. And I think this is a great thing because it gives us redundant information. So for example, if we have a camera that's looking at this truck in front of us, if we look at the first image on your left, maybe your algorithm is not able to detect that this is a truck. So having multiple views of the same object helps build confidence. And this also allows us to train algorithms which can leverage the complementary nature of these different sensors. So as I mentioned, cars, LiDAR, cameras, LiDAR, and radar each have their strengths and weaknesses. So by fusing them together, we can actually improve safety, and we can build a more robust algorithms. Great. So this is kind of the sensor side of things. But now, once we have these sensors, we want to actually understand the world. And this is, my area of research and my area of interest. This is perception, also known as computer vision. So given this sensory input, the standard approach for perception on an autonomous vehicle follows a three-stage pipeline. So first, we can detect objects. So given this sensor data, we want to be able to accurately localize where they are in the 3D world. Given this information, we want to be able to track these objects so we can associate past detections and link them together. So imagine if you take an image of a car, 1 second apart. Tracking is essentially the algorithm which allows you to say, okay, these two cars that I took a picture of 1 second apart, these are actually the same car. So we're associating past detections and making them temporally coherent. And lastly, I think this is the most interesting part of the pipeline, is forecasting. So given these tracks, and these tracks are basically your historical data of where this object has been, one of the things an autonomous vehicle needs to do is predict where it will be in the future. So essentially, given your past information about the environment and objects, we want to be able to accurately predict where each of these objects will be in the future. And this is challenging for a number of reasons, which we'll get into in a second. Okay, so first, 3D detection. And I want to talk about 3D detection in the case of LiDAR point clouds as input, because this is the most popular way in which people perform 3D object detection. So given the stack of LiDAR point clouds, we can actually train some neural network using supervised learning to spit out these bounding boxes for every object in a scene. So essentially what supervised learning is we have a human that goes through the data and annotates a bunch of boxes. And they go through and say, okay, I think that's a car, so let me draw a box around it and let me call it a car. So we have humans that put an immense amount of time and effort into manually labeling all these boxes with 3D information. And then given this information, we can give our neural networks two sets of input. We can give them the raw sensor data, and we can give them these labeled boxes. And we can ask our model to learn to predict these boxes from sensor data, so that in the field, when we want to go and deploy this model in the real world, then we can basically ask our model, given this new point cloud, predict all these boxes for me, or tell me where all these objects are. So that's essentially how 3D object detection works. Okay. So why is 3D object detection challenging? I think it's really challenging, particularly when you think about long-range detection. So imagine we have our two sensors, we have LiDAR and camera. If we want to detect things far away, it's quite challenging because in the camera, you only have a few pixels dedicated to every object. So for example, this object that I'm pointing at here in blue, that's maybe 10 by 20 pixels, for example. So we need to identify that this is a car, and we need to draw an accurate bounding box given just 200 pixels of information. And that's a really challenging problem. And similarly, with LiDAR, since we're so far away, and I think this particular object is about 70 meters away. So at 70 meters away with the standard LiDAR point clouds, we don't necessarily have a lot of information. So our LiDAR, or when we shoot our laser at this object, not a lot of the points that we send out that hit this object actually make it back to our sensor. So we don't have a lot of information about these objects far away. So 3D object detection is challenging when you want to detect things far away. And why is this important? Well, when we're driving on a highway, for example, at 60 miles an hour, you're moving really fast. So in order to perform safe maneuvers, you need to detect and understand a larger context of your environment. So you need to be able to understand that this object that's actually 70 meters away, I need to be aware of it, because that object may slow down, may speed up, may change lanes, and all of this will really impact me in the next few seconds, really. So that's why thinking about long range detection is so important. Okay, so the next part is multi-object tracking. As I mentioned, we have we have detections which we take from the LiDAR point clouds, and then we want to associate these over time. So you can see the consistent colors basically mean our algorithm is correctly identifying that consecutive bounding boxes for the same objects are actually belonging to the same vehicles. And this is a really hard problem, because this is, without going into too many details about the algorithm, this is a combinatorial optimization problem. So it becomes really challenging to make accurate assignments of, okay, does this box belong to car A or car B, when the two cars are really close to each other? So that's a really challenging problem in multi-object tracking. So again, why is this challenging? Let's take a quick example here. Let's say you want to track this car. So we're able to draw a nice bounding box around this car at the first time step. And let's say this car moves behind this tree. Now we can no longer detect this object. So we have these occluders which prevent us from accurately detecting and associating the previous detection with the current position of the car. And when the car shows up at the other end of this mini forest, now you're able to redetect this car. But now the most important question, which multi-object tracking is trying to ask, is trying to associate these objects or this box detection from the first time step, which I showed you before we entered the trees, and the last time step once we exit the trees. So that's why multi-object tracking is quite challenging. And lastly, we have motion forecasting, which takes these input tracks. These input tracks serve as a historical trajectory. And given this historical trajectory, we want to predict how the world will unfold. So in green, we see the projected trajectory of this red agent here. So let me play that again. So we have these tracks which allow us to predict which allow us to understand the history. And given the history, we want to predict how these objects will move in the future. And again, this is important for understanding the intentions of other agents. So if we want to make a left-hand turn, we can't make a left-hand turn if someone else wants to drive straight in front of us, right? So understanding the intentions of other drivers is really important, and it's something that we can do naturally. So the important thing is this three-stage pipeline happens automatically for humans. And when we want to try and explicitly build out autonomous systems to perform these same actions, there's a lot of important considerations which we have to take into account. Okay, so that's multi-object forecasting. And why is this challenging? So imagine you're the ego car here, and you have all these agents in the scene. You have pedestrians, cars, bicycles, and you want to predict how each of these objects are going to move. And the important thing here is that predicting the future is really challenging, because it's the future, right? It's really hard to predict the future. So the future can unfold in multiple ways. So for example, this pink car could go straight, it could take a right, So there are multiple features which you need to consider, you know, and you need to be able to accurately predict these things. And again, we can just naturally do this. We understand that a car in the left lane is likely to turn left. But we need to, you know, explicitly encode and train our models to be able to reason about the world in the same way that we do. Okay. So now this is kind of the summary of these, you know, the sensors and algorithms which we use for autonomous systems. So as I mentioned, you know, up until now, well, we've really been talking about, you know, how we're going to get to full automation. So we're not fully there. We're somewhere between level 3 and level 4. But if we want to get to level 5 automation, there's a lot of work that still needs to be done. So the work that we need to do to get from where we are today to where we want to be, these are all really interesting research questions, and this is some of the things that I'm working on. So I want to briefly talk about some of the research questions that I've been thinking about and why I think these are so cool and interesting. So I think something we can all agree on is that the world is more than pedestrians and cars, right? So when you're driving out in the world, obviously the majority of things you see are people and cars. But if we want to build safe autonomous systems, we really need to be able to detect all the weird things you might encounter in the real world, right? So even if you've only seen like a push cart once before in your life, you still know how to detect and react to this push cart, for example. Okay, so we agree that the world is more than pedestrians and cars, but the weird thing here is that most data sets actually ignore these rare classes. So obviously we have a few things that happen with these data sets. So we have a canonical set of standard classes, which we benchmark, which is great, which includes mostly people, cars, buses, bicycles. But again, the world is much more than these things. So when we think about these rare classes, this brings up a concept called the long tail. So you can kind of imagine that, and this is on a logarithmic scale, by the way. So there are certain things that you only see very few of, like you know, wheelchairs and emergency vehicles. But it's still important to detect these objects. So it turns out that most data sets simply just ignore the tail. They ignore this long tail problem, and they really only focus on cars and pedestrians. So the good news is we have really good car and pedestrian detectors, but the bad news is we have really poor wheelchair and you know, stroller detectors. And I think that should be, you know, cause for concern, because if we want to build safe autonomous vehicles, we should really be building better wheelchair and stroller detectors, right? So one natural question is, you know, why should we care about the long tail? So as I mentioned, detection allows us, thinking about long tail detection allows us to get a fine-grained scene understanding of the environment around us. Tracking these detections helps us build a coherent understanding of how these objects move. And given this information, we want to be able to accurately forecast these objects. So for example, it's important to distinguish between children and adults and not just lump them together as pedestrians, because children move differently than adults. And in fact, children probably move more erratically or sporadically than an adult. So we want to build larger safety margins when we're driving around children. And you know, going back to the example of distinguishing between cars and police cars, when you're building your motion planner and you want to actually drive in the real world, you should treat cars and police cars differently. Because if you see a police car behind you with its lights on, it's important that you move aside and you you know, give way. So this is something that we need to encode in this autonomous system. And really, the only way we can do this is by really thinking about and wrestling with this problem of long tail detection. So thinking about and embracing the long tail really starts with you know, thinking about how do we build better detectors for the long tail. So that's one of the research problems which I'm interested in. And long tail 3D detection is really difficult. So in the chat, I want to encourage you. We're looking at these two blue boxes, and these are the LiDAR returns for these blue boxes. I think it's a great idea for you guys just to throw out a few guesses. What are these blue boxes? and I'll pause for 10 seconds to give you guys a chance to think it over. So this is multiple choice. Cool. So let's assume you guys have put in your guesses, and now I'll show you what these objects actually are, and these are actually people, right? So the crazy thing to me, and the thing which I still have a hard time wrapping my head around, is that we're able to build LiDAR detectors that are able to look at like 8 points on a person. So we're able to see, like, for example, we have 8 points on this pedestrian, and we're able to detect them and call them pedestrians. So that's why, working with LiDAR is really hard because of these sparse points. So it's really hard to tell the difference, for example, between an adult and a child given 8 points. But we can do a better job with RGB and cameras. But as I mentioned, working with cameras is a little bit challenging because we don't have good estimates of depth, right? So we need both things here. We need to be able to accurately detect and localize these objects, and we need to be able to accurately classify them and understand what they are. So this basically shows again the complementary nature of these these sensors. And part of the research work that I'm doing is really trying to push forth that we should really be building multimodal algorithms. So a lot of the algorithms we have, they exclusively work on single modalities. But if we really want to embrace this long tail detection, we should be thinking about multimodal fusion. Okay, so that's the first area of research interest. And the second thing is really thinking about this whole autonomy stack. So as I mentioned, we have 3 stages in our autonomy stack. We have detection, tracking, and forecasting. And the way that it's currently built out is that we first detect objects. We have a model for that. Then given all of these detections, we pass that on to our tracker. We have a model for that. So we track all of these objects, and we pass that on to our forecaster. So and then we have a separate model for that. So one of the issues with the stage-wise approach is that you actually have compounding errors. So if you fail to detect an object, there's no way you can track it, and there's definitely no way you can forecast it, right? So mistakes earlier on in the pipeline are difficult to recover from later on in the pipeline. And the research community has segmented each of these problems into their own research areas. So we have people working on detection, people working on tracking, and people working on forecasting. But rarely do we see people actually integrating all 3 of these pipelines to build something end-to-end. So studying each of these problems in isolation actually hides the difficulty of integrating all of these submodules. And the interesting thing here is nearly all autonomous vehicle companies adopt this stage-wise approach. So one of the research questions is this really the best solution? And my answer to this is, I don't think so. So one of the things we can do is directly forecast. So given the sensor input, we could train a neural network rather than going through these 3 stages. We can actually directly go and predict the object locations and future forecasts of these objects. So we have some recent work that explores this exact idea. So this, I think, is a really exciting area of innovation that could potentially change the stack or the way in which we build autonomous vehicle stacks. So that's something that I think is super interesting and very cool. So I want to end on kind of a call to action, where we have a lot of interest from people that want to work in work on autonomous vehicles. And I think that's exactly the right thing. So if you're interested on working on autonomous vehicles, we want you to come join and get involved, get your hands dirty, and help us build these pipelines. So working on autonomous vehicles is such a challenging problem. And as we've seen, it's taken us 33 years, or it's been 33 years, and we're still trying to close the gap between that 1.8% of driverless autonomy that we've been missing since 1990. So we can always use smart people like yourselves And we need a diversity of ideas and people to help us build the next generation of autonomous vehicles. So thinking about all these research questions, I hope that I've kind of inspired you to think about these interesting and important challenges in autonomous vehicles. So although we're seeing big headlines about autonomous vehicles in the real world, this is by no means a solved problem. So we need people like you to come join us and think about these challenging problems. So in the spirit of thinking about challenging problems, I want to hand it off to Rayna, who's going to go through an activity to help you guys also think about some of the challenging moral questions we need to ask when building autonomous vehicles.
Thank you. So I'm going to talk a little bit about the ethics of autonomous vehicles and some of the questions and thoughts that people have had with the recent developments that we've had with these vehicles. So like Neehar said, the cameras, all the sensors, those are ways that a vehicle sees the world. And after they see it, they have to make the decision of what they're going to do once they have the information. So when we drive as humans, we take in all of the information, all of our lessons we've learned in maybe driving school, in life, and we make the decision of when to stop, when to slow down, when to go forward, all of that. And so some part of it is that in 2019, Uber's self-driving vehicle caused a fatal crash between a car and a cyclist. Now, in this car, there was a driver that can take over at any moment in the case that there was something like this happen. But the crash was labeled as avoidable if the driver had taken over in time, which they did not. And this shows that the autonomous vehicles are not ready to be fully independent. So this raised the question of people are asking if we can trust these vehicles. And in order for people to adopt autonomous vehicles, we need people to trust them. So people are asking questions about the ethics regarding its autonomy and safety of others around the vehicle, but also the person inside the vehicle. And the reason why I find this question is a little pretty interesting is that I work on helping blind pedestrians navigate urban crosswalks. So when these people, if they do not go into the intersection correctly or they veer off because of some noise, they are now stepping outside the bounds of the crosswalk, which an autonomous vehicle would have to understand if they do not get back in time. And so just a way of thinking about this is it's called the trolley problem. It's an ethics question. So this goes is that you are the conductor of the train and you see ahead of you, there are 5 people tied to the track. You see that there's a lever that allows you to switch tracks, but on that new track is a singular person tied to the rail. Would you consciously change tracks, effectively killing the one person to save 5? Or would you let the train take its original course, killing 5 people, but knowing your actions save the problem? Now, pretty morbid thought, however, and there's no right answer to this. People have been debating this using different types of ethical thoughts in different ways. And so to apply this to a autonomous vehicle, we need to think about, can extreme traffic conditions be programmed? So in the first picture below, there are 5 people or 3 people and a dog, and the car is heading straight for them. The car can either make a decision of turning into the barrier that could effectively injure the person that's inside the vehicle to save the lives of 4 others, or it could keep going, injuring the 4 people. And so one of the questions is, what would the decision of the driver, if they were driving, make? And also, can a car even make a decision of deciding to hurt the person inside the vehicle instead of hurting the person that's walking across the crosswalk? And should we be able to even pre-program these vehicles' decisions? Or should machines even try to learn these situations? So here's a little kind of it's an experiment, but it's also a way for you guys to learn about these scenarios. So it's called the moral machine. And if you want to keep going on your own, I'll go through a couple of them, but what you have to do is click on the link, and then you would go to these, click on classic, and that would let you test out a few scenarios. And that also, like when you do this, know that there's no correct answer. It's just a kind of a fun way for you to make decisions, think your thought process out. I'll go through a couple of them and show you my thought process on them. But yeah. And so you go to classic, which is at the top. And then, so the first one is the question that the trolley question. So there's 5 people. If the train keeps going straight ahead, you would kill the 5 people. And if you turn, then you would kill the 1 person. Please do not judge me on this. This is just what I would say. I would basically turn and kill the 1 person to save the 5. Now, there are certain scenarios that are tested, showing that, maybe that 1 person was actually a really good person and the 5 people were actually doing bad things. Who knows? But you don't know what the person's situation is. So I would make the conscious decision to turn. So yeah, if you just click on your scenario that you want, you would go on to the next one. Yep, that one. Same kind of question. I'm pretty sure this is the same thing, but would you change tracks? I again would say I would change tracks. So in this scenario, there is 1 person that is lying there, and if it says a man in the blue is standing in the footbridge over the railroad, it's so moving fast that anyone who hits it will die. Ahead of there are 5 people. The person on the bridge would weigh enough to kill the person, but to stop them, effectively saving the 5 people. I would not consciously decide to push someone off of a bridge. And so I would go with the scenario on my right. And it makes you, this is literally, this is also a way for the people who created this to understand other people's decisions. But if you want to keep going, then you could keep going. There's also a design where you can design your scenarios up at the top. And so it basically lets you decide. So, I could say this is a pedestrian versus pedestrian scenario. And you would click on one of the choices. So I would choose pedestrian versus pedestrian. And then, legal complication. Is the person jaywalking? Is it their green light or is there no light? And so scenarios like that, and the car has to make the decision. I'm not going to go through all of them because I want to give people a chance to think of their own creative scenarios, but this is a really fun way for you to understand some of the decisions that people have to make, and cars have to make on a daily basis. And so I think we can take questions now.
Okay, I see a question. Okay. How do we associate the object detected in the image with that detected on the LiDAR output? Okay, so this is a great question. And this is about sensor synchronization and sensor calibration. So you can imagine if you have a camera looking straight ahead, and you have your LiDAR detector or your LiDAR, which is a 360-degree sensor. It can also see the same region in front of you. So, you can bring your detection for the camera and the LiDAR into the same frame of reference. So once they're in the same frame of reference, now it really doesn't matter that one of the detections came from a camera and one came from a LiDAR. And once you have these 2 detections in the same frame of reference, you can, perform your fusion algorithm. Hopefully that answers that question. Okay. Any other questions?
Abdul Rahman, I agree with you. This is the best talk ever. So I want to congratulate Neehar and Rayna. So leaning into Abdul Rahman's question here, thinking about it, autonomous vehicles, getting engaged in robotics can seem really, really overwhelming. So I want to address this question here, and I wonder if you both might talk about how to get started, how to get engaged, because it's not that we were each, you haven't been perhaps studying autonomous vehicles for 5, 6 years, but there's incredible resources there, and there are pathways. Carnegie Mellon has a very special role with autonomy, and specifically with autonomous vehicles, but there are so many opportunities out there. So let's turn to this question here, and then Rayna and Neehar, if you maybe provide some advice and guidance on getting started as well, that would be fabulous.
Absolutely. Rayna, do you want to go first?
Yeah, sure. So for me, I just heard about the RISC program, and I've always been interested in robotics. So this was actually a really great way for me to start and kind of start in the field. But in high school, I did a lot of robotics, and then in college, I took an ethics class, hence why I gave the ethics portion of the talk. But just take classes that interest you in college and high school. Take online courses, a lot of them out there for free. So that'll give you a little bit more insight and a little bit like a quick overview on robotics part. And then for getting, started, I say that the RISC program, there's a bunch of other programs out there too, but something special about the RISC program is, for me, is that it's not just about learning and doing research, but it's also people sharing their ideas, and it's a big community part. So Neehar can probably speak to this part too, but you learn a lot more things that are outside your field in the RISC program, and just attending some of the talks, that the RoboLaunch talks, that'll help you too. So that's my advice, is just, be curious, be, super excited about it, and just do your research, and then look at what you want to look at.
Great. So I actually have an interesting story about how I got into RISC, came to CMU and started working on autonomous vehicles. So when I was, I think, a sophomore in college, one of my friends told me about, hey, there's this lecture that one of these professors from CMU, he's giving a talk on autonomous vehicles. It's like, okay, cool. But this is during the same time as one of my probability classes. So I skipped my probability class and I went to lecture. Don't tell anyone. So I skipped my class to go to this lecture, and I sat through the lecture and I was like, okay, this is super cool stuff. I want to get involved. So what I did after the end of this talk was I went up to the speaker, and I told him I've been thinking about getting involved with research. I think this is a super cool area of work. I'd like to get involved. So the important thing is that you just have to ask, and opportunities will present themselves. So I spoke with this professor, and he said, sure, I'll take you on board, and we'll do this through the RISC program. So just because I decided to go to this lecture and I stayed after and I asked a few questions, I was able to get into the RISC program. And because of RISC and because of these prior experiences in robotics, when it came time to apply for grad school, I wanted to continue working with the same professor that I worked with, during RISC, and because I had the network and I had the experience and exposure from RISC, I was able to successfully apply to Carnegie Mellon. And now my academic PhD advisor is still the same guy that I went up to him as a sophomore in college, and I asked him for an opportunity to work with him. So I think the most important thing you can do is just get started. There's no right way to get started. When I started working in computer vision and robotics, I remember the first time that I started, I had no idea what I was doing. So I literally spent a week just watching YouTube lectures from Stanford on computer vision. And I basically got up to speed as fast as I possibly could. So my foundational knowledge on computer vision is not through like a structured mean, taking a class, but rather just ad hoc, trying out new projects, building stuff, getting stuck, googling stuff, Stack Overflow, forums, figuring stuff out, and that process really showed me that research was a super interesting, viable, and vibrant career. So because of these formative experiences in undergrad, That's why I'm doing a PhD in robotics and computer vision today. So just get started. There's no right way to get started, and just be curious, ask questions, get involved, and there are tons of outreach events like this. Go to those. See how and keep asking questions. So people have all kind of traversed the same sort of path. So no one is born being a roboticist and being a computer vision scientist. So we've all had to take a path to get to where we are, and I'm almost certain that everyone is willing to talk about their path and tell you the things that went well for them and the things that didn't go so great for them. So leaning on your community is another great way of getting involved and understanding if this is something that you want to pursue.
Neehar, we're so happy that you chose to attend the talk rather than your probability class, and we hope
Me too.
you're even if your probability instructor was watching right now, I think they would be pleased with the outcome of it as well. And I'd like to lean into those comments. Please attend as many things as you can, and not just with RIS or RoboLaunch. This is an example of there's so many programs out there that they want to have conversations they're looking for, and are you and Rayna, you both raised something in your sharing your experience that I think is so powerful, is that you didn't have, maybe through your own lens or eyes, the perfect profile, all this research experience and other things. It's about getting started. And as part of the RoboLaunch experience this summer, we intentionally chose to highlight faculty members from around the world, right? And across the US, and only a few from within CMU. This fall, we'll be having conversations with faculty members at Carnegie Mellon within the Robotics Institute. But through RoboLaunch, that we're highlighting, there's a lot going on around the world, and there's so many opportunities, and it's preparing for it and reaching out. I love that you also said you looked at the Stanford materials online, to get ready for your research at the Robotics Institute. That's exactly it. It doesn't matter if it's from Carnegie Mellon, MIT, Stanford, your home university, whatever it is. There are materials and there's things out there then that you can explore to get on that path and work toward futures in that. And Rayna, you talked about the community. We work within the risk cohort during the summer. It's about that community, not just for those 10, 11 weeks, but it's for a lifetime. And we hope that through risk, the scholars that participate, that you're going to stay connected and help each other and, just build a dynamic community of support that you can lean on throughout your career, but also as friends as well, to navigate things. So I want to thank you both and turn it back to Neehar and Rayna so that you can talk about this activity here.
Yeah, absolutely. And I see there are a few other questions online, so I guess maybe we can quickly go through and answer those as well.
Absolutely.
Sure, sounds great. How do systems work during special weather? Yeah, so that's a great question, and one of the ways we get our systems to work in special weather is to gather and collect training data in this special weather. How much data do we need in the supervised learning process? More data, the better. That's usually how deep learning goes these days. If you have more data and more compute, you can usually make better, better models. Can two cameras measure depth? Yes, they can, but that requires the right calibration, and it's still challenging to get accurate estimation at long distances, especially if your calibration matrices are not perfect. Okay, great. Thank you so much.
Okay, Neehar and Rayna, are there any concluding remarks or anything that you would like to say before we wrap up today?
I
I
guess,
think
I think we kind of covered it, but.
Yeah, you did. You did a fantastic job. You did a fantastic job. This will go live. So I do want to let everyone know that this will go live, and we can continue to add your comments and suggestions are welcome there for Neehar and Rayna. And if there's resources that we think of or we can add to the description in there, we'd be happy to do so. So congratulations to Rayna and Neehar for a fabulous presentation. This was such a wonderful introduction, and we look forward to sharing this with many more students. So see you soon. Take care.